Chapter 5, slides 21 to 32. We've now spent some time understanding how to identify a stereocenter, and this is going to help us in understanding the chirality of an entire molecule. Okay, we've got a little bit to go though, so I'm going to go back to relationships. When we have chiral molecule and we have another molecule we're comparing it to, sometimes it's difficult to, as I mentioned in all practicality, to try and envision those two molecules overlaying on top of one another and seeing if they're superimposable or non-superimposable. That's a really tough thing to do. So we're going to define the two types of stereoisomers that there are as enantiomers and diastereomers. And unfortunately, their hard and fast definition talks about them relative to mirror images. But I'm going to show you some shortcuts, so don't get too scared by seeing these definitions. Okay, so let's cover the two types of stereoisomer relationships. And again, we're going back to relationships. We're going to be comparing two molecules. The first thing you should do when you compare two molecules is to check to see if things are connected the same way. If they're connected completely differently, you don't even have to worry about enantiomers and diastereomers. The connection, if different, is constitutional. But if things are connected the same way, and they have the possibility of having differences through space, you now have to decide whether or not it's the same, right? So you want to check the relationship if they're the same. And if they're chiral, then you're going to say, well, probably not the same. They're probably non-superimposable stereoisomers. Because remember, if the two things you're comparing are connected the same and are superposable, then they must be the same molecule. But if the two things are connected in the same order but non-superimposable, now you're talking about stereoisomers. So order, check constitutional framework. If the same, then check to see if there's chirality to the molecules. Check for those stereocenters. And if you don't find any stereocenters, then they're probably the same molecule. If you start seeing stereocenters, then you're working your way towards stereoisomeric relationships. And there are two types, enantiomers and diastereomers. So enantiomers are two molecules that are not superimposable, but they are mirror images. Okay, so very specifically, when a molecule has a mirror image, and you take that mirror image out of the mirror and try to overlay it, it is not superimposable. Okay, so I'm going to draw, I just want you to see, this is the mirror. And I want you to see that I drew it like its mirror image right now. But what I'm going to do is I'm going to redraw this molecule. And I'm going to do it by pancake flipping it. If I pancake flip it, then what I'm going to see this is not the same flipping that we did in chair flips, right, where you're actually twisting. I'm actually taking the molecule and flipping it around. And what I want you to notice is that, and I'm going to go over this again in the future, but what I want you to notice is that if you keep the carbon backbone exactly the same, you keep the carbon backbone in the exact same orientation, and every wedge becomes a hash and every hash becomes a wedge, you are probably dealing with enantiomers. Okay, so that's the first step. That's going to help us when we look at much larger chiral molecules. But I just wanted to point out that these two molecules that I've circled here, these two are the same. They're just drawn differently. Okay, And if you try as much as you want, you try to overlay it so that A and B overlay, no matter what you do, things are not in the same trajectory. This is a relationship called enantiomers, when the mirror image is not superimposable. Why is this important to know? Well, take Carvone, for example. If you have R Carvone shown here, where the stereocenter, there's one stereocenter, so that's why you only need to tell it one R. And on the other side, you see the stereocenter is S. It's a completely different orientation. You can practice your IUPAC naming and prove to yourself that these are named appropriately. But what you'll notice is that there are differences between these two molecules. For these two specific molecules, the biological activity and the optical rotation is different. What you also notice is that everything else is the same. So if I had a mixture, let's say I had a beaker, and I had a 50-50 mixture of these two molecules in the pot, what you'd find out is that you'd never know you had a mixture, because when you took the melting point, it wasn't even that there was some other molecule that was slightly impure, and you would not see a melting point depression, right? You'd get this 25 degrees. The boiling point, 231 degrees. The polarity, let's say you took a TLC of this 50-50 mixture. Now, normally if you have two different molecules, you'll see two spots. But unfortunately, after you run this reaction or this TLC, you'll only see one spot because the polarities are the same. The refractive index is the same. The density is the same. The solubility is the same, on and on and on. So how the heck did we know that enantiomers are different molecules if everything that we do to test them seems to be one molecule? Well, there's two differences. Notice that how they react biologically are different. One of them smells like spearmint and the other one like caraway seeds, like rye bread. The other thing that you'll notice is that, and this is crazy, someone decided to test how it rotates plane polarized light. And what it found is that it rotates plane polarized light -61 for one enantiomer and +61 for the other. So optical rotation and biological reactivity, meaning how it interacts with substrates and such in our bodies, is the only way you can figure out that you've got enantiomers. Holy mackerel, that is tough. Well, instrument-wise, we have to use a polarimeter to see that we have a mixture or a pure sample of an enantiomer. How this happens is that you use a sodium lamp, right? So just a sodium light bulb. This is a special instrument that we have called a polarimeter. And it's shining light of all wavelengths, right, in every direction. So you've got all the wavelengths of the sodium lamp going in all random directions. That's what is indicated here. So you can use your hands to see, okay, you've got all these wavelengths and they're going in all these different directions. But then you polarize the wavelengths using a polarizing filter. So you've got these slits. So only the wavelengths that are traveling in the same orientation as the slit can go through. So now you have plane polarized light, meaning only the ones that are traveling in the same direction or orientation as the slit, your polarizer, will be allowed through, okay? And then in a chamber, this is the sample cell, you actually create a solution of the molecule of interest. Let's say you had what you thought was a clean, pure, you only had R Carvone. You thought you had a pure R Carvone. So what you do is you dissolve the R Carvone in a solvent. You have to be very, very, very specific about the concentration, how many grams per milliliters of the solvent, that's C. So if you know that, because you make up you make up your own solution. So you know exactly what the concentration is within the sample cell, and you inject the sample cell with your solution, which hopefully only has the one molecule in it. If the molecule is chiral and pure, it will have a specific rotation. What it'll do is it'll take that plane polarized light, and as that light travels through your sample cell, that solution, it will turn the light, right? It will orient the light either positively from 0 or negative, so that that wavelength will actually change. So if it's going straight up and down, you'll see that the plane polarized light will either go positive or negative in one direction. You can't predict it. You can just experimentally take the specific rotation of a given molecule, and then it becomes sort of a property of that molecule. That molecule, like our carvone, rotates plane polarized light by negative 61 degrees. But what's interesting is that the enantiomer is always the same number of degrees, but of the opposite sign. So you'll notice that S-carvone rotates plane polarized light by plus 61 degrees. So if you know that property of a given molecule and you want to test to make sure that you have a pure rotation, a pure molecule, then you can test it in the polarimeter to see if you have just the one enantiomer. What would happen if you had a mixture, a 50-50 mixture of R and S carvone? Here's another example. I have R 2-methyl-1-butanol with an optical rotation of plus 5.75 degrees. If I had the S, or the enantiomer of the same molecule, the optical rotation would be negative 5.75 degrees. When you have a 50-50 mixture of enantiomers, this is called a racemic mixture or a racemate. So very specifically, a 50-50 mixture of enantiomers is called a racemic mixture. If I had a racemic mixture and I put it into my polarimeter, what would the optical rotation of the racemic mixture be? 50-50 mixture. One rotates light plus 5.75, the other one negative 5.75. You would see 0 degrees. So if you had a 50-50 mixture of two enantiomers, you would get, of the related enantiomers, right? You would get 0 degrees of a rotation, nothing. When else might you get a 0 degree rotation? Well, if you said achiral molecules, so an achiral molecule, even if you had just one pure sample of an achiral molecule, say, I don't know, for an example, like propane. Propane doesn't have any chiral centers, right? It's an achiral molecule. If you put it in a polarimeter, even if all you had was pure, pristine propane, you would see a rotation of 0 degrees. So achiral molecules do not rotate plane polarized light, and a racemic mixture, a 50-50 mixture of enantiomers, because of their equal but opposite rotation, also you'll see 0 degrees on the polarimeter. A measure of when you have a mixture outside of 50-50, this is reported very specifically in the literature as an excess, an enantiomeric excess, or EE for short. Let's say I ran a reaction and I got a 30-70 mixture of the R to S respectively. This mixture would be reported in the literature as an enantiomeric excess. And the way that you do this is you calculate the difference between them. What's the excess between them? So you take the difference between them and then you divide it by the total, right? And so the excess is 70, right? So you've got more 70 than the other one, 30. So what you do is you take the absolute value difference. So it doesn't matter, 30 minus 70, 70 minus 30. You basically are just taking the absolute value between them. So 70 minus 30, right? The absolute value of 70 minus 30 is 40. You take that number and divide it by R and S. So this is 100, right? Overall, the excess is 40 over 100. 40 divided by 100 times 100 gives us the percent EE, in this case, of 40%. So the higher the EE, the better the mixture in your favor. Hopefully it's the one that you want of the two. It is very tricky. Just to imagine it. Imagine trying to make one of these molecules and not the other one. Think about how you have to construct something through space to get only one of them and not the other. You think you might be doing really well with a 70-30 mixture of favoring one over another, but a 40% EE is actually not very good. In many papers, you'll read of the state-of-the-art syntheses where people are generating one enantiomer over the other in, 98% EE and above. Think about that. That is pretty darn amazing. And you know what the best scientist is for making one enantiomer over another? That would be our own bodies, right? Our own bodies are super specific when they make molecules. And I wanted to draw your attention to some terminology you might see in some other courses. Dexrotatory and levrotatory. So I know that when you guys are taking a biochemistry course, when you see an amino acid, you talk about the natural amino acids and the non-natural amino acids, right? And what's funny is that they don't actually call them R and S. You guys now have a beautiful way to communicate one type of stereoisomer over another. Unfortunately, in biochemistry, they use the terms D and L. And D and L are actually related to the rotation of light. When you rotate light positively or dexrotatory, it's D. And when you rotate plane polarized light negative, it's levrotatory. The positive and negative nature of rotating of the light by one stereoisomer is completely generated by experimental. You guys, there's no way that you guys can determine if something is D or L without having the optical rotation given to you. And since optical rotation can only be determined experimentally using a polarimeter, this is not a very handy way to name molecules, right? It's so much nicer to be able to assign things S and R because you guys with our priority groups can figure it out. If someone tells you they have the D 2-methyl-1-butanol, you'll just have to look it up or memorize it because there is no relationship between D and R. You could have a dexrotatory S relationship. You could have a dexrotatory R relationship. You could have a levrotatory S molecule or a levrotatory R molecule. D and L have no direct relationship to R and S. R and S are what we use for IUPAC naming only. D and L are based on an old school polarimeter rotation of light that you have to just judge by experiment and or look up. So you will not see me use D and L in this course. I find it very difficult to use. We will be using R and S specifically. Okay, so enantiomers have everything about them is the same. Boiling points, melting points, polarity, solubility, everything, except for how they interact in the body and how they rotate plane polarized light. So what's a diastereomer? Well, a diastereomer is also a molecule in relation to another molecule that is not superimposable, thus it falls under stereoisomers. However, it's not the mirror image. Okay, so it's not a mirror image, but yet it's still not superimposable. That's a tough definition. And I'll show you a way that makes it a little easier to decipher, and we'll do some practice together. Diastereomers, unlike enantiomers though, have different everything. They have different boiling points, different melting points, different polarities, different refractive indices, different densities, different biological function, different optical rotations. So for optical rotations, you might see one diastereomer be plus 5.7. You might see another one be minus 5.1. You might see maybe one diastereomer is plus 10. The other one might be plus 3, right? They're completely different. They have no sort of rational way to assimilate them. Unlike enantiomers, which are equal but opposite in sign, diastereomers are they're totally different. If you had these two molecules, A and B, and you took a TLC of them, because they have different polarities, you might actually see two spots very close to each other, but you'll see two spots. Diastereomers in every way can be distinguished from one another. They can be seen as different. Everything, it points to the fact that you have a mixture. Enantiomers are tough because if they have the same everything, it looks like you're just looking at one molecule. This is very important when you look overall at relationships. And as I mentioned before, let me go back to enantiomers. The relationship of enantiomers. Think about it. If a scientist is making a molecule, and the molecule they need to make is a drug, and the drug needs to have very specific through space orientation to fit into, say, an enzyme pocket. In order to do the job, that drug needs to be made very stereochemically specific. There's been lots of incidences in the literature and in history where a molecule with one enantiomer of a molecule may end up helping and being the drug of choice, but its enantiomer is sinister and actually has a lot of the bad, side products or side reactions with your body. An example of that classically is thalidomide. Thalidomide was made enantiomerically pure, but when it was taken in the body, our body actually racemizes or converts one to the other enantiomer. And the enantiomer of thalidomide caused massive problems. Thalidomide was originally marketed towards helping pregnant women with their morning sickness. Unfortunately, when the body took in thalidomide and converted one enantiomer to the other enantiomer wreaked havoc and caused massive birth defects for those mothers taking the drug. And so we have to be very careful about these molecules and making sure that when we are making one molecule enantiomerically pure, that it is that molecule and stays that molecule. Otherwise, to massive detriment. So it's important to understand the relationships between different molecules as well. And I also want to show you what happens when the molecules get bigger. How can I look at two molecules and decide whether or not they're enantiomeric or diastereomeric? First, it's important to understand statistically how many different ways you can draw a stereoisomer. So for every stereocenter, for every chiral center, N, you can use the 2 to the N rule to figure out how many stereoisomers there are for that given molecule. So let's take a look. Let's use cholesterol as an example. How many stereocenters can you count in cholesterol? So in order to figure out the maximum number of possible cholesterol isomers, I have to count the stereocenters. 1, 2, 3, 4, 5, 6, 7, 8. There are 8 chiral centers for cholesterol. So it's 2 to the 8. What is that? So statistics tells me that there are 256 different ways to make a cholesterol molecule from a stereoisomer perspective. How do I draw the enantiomer? Okay, so here's the trick, okay? Drawing the enantiomer, which is also the mirror image, can be very tricky if you're trying to actually draw the mirror image. Okay, don't do that. Here's my rule of thumb. Draw the framework of the carbons exactly the same as the one you're given. So I've got cholesterol written here. So I'm going to draw the framework exactly the same. I'm just going to leave out the stereo centers. Okay, so I've drawn the framework exactly the same. Okay, now each one of those stereo centers has a wedge or hash on it. And what I'm going to do is I'm going to invert them. So everything that's forward is going to become back, and everything that's back is going to become forward. So I draw back OH, back methyl, forward hydrogen, back hydrogen, forward hydrogen, back methyl, forward methyl. That is the enantiomer. Keep the backbone the same, in the same orientation as it's given to you, and completely invert all of the centers. Let's go back to that first slide. Do you remember when I did this earlier? You take molecule A and you look at the backbone. If I draw the backbone exactly the same way, I then invert each center. If both of them were forward, then on my other one, both of them are back. Notice that the backbone was not drawn exactly the same when you draw it in a mirror image. The mirror image is looking at itself in the mirror, and so the backbone looks a little different. So that's why the wedges were on the same side. But if I pancake flip it and make the backbone look exactly the same, what I'll notice is all the wedges become hashes. Everything that was in the front is now in the back because I've pancake flipped it, and everything in the back becomes forward. So this is a very quick and easy way to draw the enantiomer, no matter what the size of the molecule. If you can just copy the molecule structure as is, keep everything the same, the 6 to 6 to 6 to 5 to chain, do it the same way over on the right-hand side. All you need to do is invert every single center. Okay, how about diastereomers? Diastereomers, so if this is one molecule, if this is one molecule, this is one stereoisomer of the 256. Its enantiomer is the second stereo. I've just drawn 2 stereoisomers of the 256, okay? The 254 remaining are all the other combinations, okay? So a diastereomer, and again, you can keep everything the same. Keep everything the same. And then you have a choice. All the remaining 254 are all the statistical differences that are possible. If I change every single one, I've drawn an enantiomer. If I flip every single stereocenter, it's an enantiomer. Any combination of change, though, without flipping all of them, right? So how many did we count? We counted 8 stereocenters. I could change 7 of them. I could change any 6 of them. I could change any 5 of them, change any 4 of them, any 3, any 2, any 1. Maybe I change the alcohol. I flipped it from, see, I started out in the forward, now it's in the back. And if I keep all the other ones the same, kept all the other ones the same, but I changed 1. That's a diastereomer. I could change any 2, any 3, any 4, any 5, any 6, any 7. I can't change all 8 though. I've already changed all 8. That's the 1 enantiomer for that. Okay, so that's the trick. That's your little cheat without having to try and maneuver your brain to draw a mirror image for something. I'd like you to practice this. This molecule, 3-bromo-2-butanol, has 2 stereocenters. 2 to the 2. Therefore, how many stereoisomers can you draw for this molecule? And then I'd like you to name them. Let's go back to some relationships. I want you to recall that chirality of a molecule, which we haven't really discussed in a bit. Chirality is when you have at least one stereo center and no internal plane of symmetry. Okay, so I want to come back to the chirality issue. How do I determine if a molecule is chiral or not? We started doing that because we started to learn how to identify a chiral center. And we started to look at relationships between different stereoisomers, diastereomers and enantiomers, okay? But there's one thing that I haven't talked about yet. We haven't talked about internal planes of symmetry. So I want to use this slide to bring up this point. I have listed 3 molecules, A, B, and C. The first one is tartaric acid with 2 stereocenters, R and R. So it has stereocenters. B is SS tartaric acid. It also has stereocenters. And C is 2R, 3S. Okay, 2R, 3S. It also has stereocenters. So all 3 of these guys have stereocenters. So if you look at A, let's just look at the first row here, A. It has a melting point of 171. It rotates plane polarized light plus 11.98, and its solubility in water is 139. Okay, let's look at B. If I just gave you A and B without any data, look at them and tell me what their relationship is. If you said that they were enantiomers, you'd be correct. They're enantiomers. Notice that B has the same melting point. It's the same rotation, but in the opposite direction for plane polarized light. So now what we've got is definitive evidence to say that these 2 guys, A and B, are enantiomers. So check this out. In the last row right here, plus minus means racemic mixture. So the racemic mixture, A plus B, plane polarized light, 0 degrees. Melting point changes because you've mixed them, but it doesn't depress. That's also interesting. But it's exactly what I said. Racemic mixture, 50-50 of the enantiomers, plane polarized light is now 0. What's the relationship between, I don't know, B and C? Look at the carbon framework, right? The carbon framework. When we look at the carbon frameworks of each of these, you'll see from A to B, every OH was completely opposite. That's why they're enantiomers. But notice that the OH here is different, but the OH in the back up at the top is the same. Therefore, not all of the centers are inverted given the same carbon structure. These are diastereomers. B and C are diastereomers. And that makes sense because when I look at C, you'll notice that it has a very different melting point than A and B because its relationship is diastereomeric. It's different. It has a different solubility. It's different. But what's strange is this. That 0 degrees rotation. It has two stereocenters, right? Shouldn't it be chiral? Shouldn't it rotate plane polarized light just like the others did? Even though it's a diastereomer, diastereomers, right? This is the relationship B and C. Why? C looks to be chiral to me. I don't know why it's giving me a 0. And that is because we haven't talked about internal planes of symmetry. So far, I've only given you molecules that had stereocenters that happen to be chiral. But there is one more check we have to do in order to definitively put our stamp on whether or not the molecule is chiral and going to rotate plane polarized light. And this falls into the category of molecules called mesocompounds. And they are achiral. So when a compound is identical to its mirror image, it's considered to be superimposable, correct? Let's take a couple examples. Both molecules below have two chiral centers. Let's highlight them. Carbon here and the carbon here are both chiral centers. The carbon here and the carbon here are both chiral centers or stereocenters. Okay? But the molecule on the left, this one, is a chiral molecule. The molecule on the right is achiral. So although it passed the test for stereocenters, the one on the right does not pass the test for chirality because it fails internal plane of symmetry. If you look, the methyls and the hydrogens internally, as if there was a mirror plane within the molecule, reflect one another. And so if you ever draw the mirror image of this molecule, so if I keep everything the same, but I invert, remember my little trick here? I keep the molecule in the same trajectory. I'm going to invert, put the hydrogens up and the methyls down. These are actually the same molecule. Pancake flip it, and they will overlay. They are superimposable. Therefore, it's quote unquote enantiomer, as I tried to draw it, doesn't work. It's the same molecule. So it is not a chiral molecule. Okay, so what makes one chiral and the other one not? An internal plane of symmetry. So when you're understanding that you're checking for chirality, the first step is to look for stereocenters, but you still should do an internal check for plane of symmetry. If the molecule, so you gotta have stereocenters, and you should always check for stereocenters first, okay? This is your first check. You have to do it first. It's not, oh, I'll check for internal plane of symmetry first. No, do not do that. First check for stereocenters, okay? If it passes the stereocenter test, Then you check for an internal plane of symmetry. You don't want any. So no internal plane of symmetry. And if it passes that test, so it's got to pass both tests in order to be considered, right? So you found stereocenters, check. And then I check for internal plane, check. That molecule is chiral. You can definitively put your mark on it. So a meso compound will not have an enantiomer. You can try proving it to yourself with this example here. If I keep the carbon framework the same, see the carbon framework? Let's keep the carbon framework the same. Let's make the bromines now back. That's what I would do if I was trying to draw the enantiomer, right? Keep the carbon framework the same, but just invert the stereocenters. Technically, this should be the enantiomer. However, if you, with your brain, imagine kind of rotating this molecule, you'll see that they do overlay. So therefore, they're not enantiomers because the mirror image is superimposable. Here's the other thing I'd wanted to point out. Remember, chirality is you first check for stereocenters and then you look for internal planes of symmetry. Okay? It's very important to do it in that order. Why? Because of meso compounds. Okay? Sometimes you fail chirality due to the stereocenter issue. So let's just write this down again. A chiral molecule, chirality. Number one, you check for stereocenters. Then, number two, you check for no internal plane of symmetry. Okay, so I'm going to look at these two examples. Let's look up at the top here. Does the molecule A have stereocenters? Always check that first. The answer is yes. It's got a stereocenter there and a stereocenter there. Okay, it has two stereocenters. Does it have an internal plane of symmetry? No. I mean, if I try to split this molecule symmetrically down the center and fold it, it doesn't look like it's reflective. No, it doesn't. So this molecule is chiral and it follows all the rules of chirality. So I can say that because it has two stereocenters, it has 2 to the 2 number of stereoisomers, this being one of them, and there should be 3 more. 1, 2, 3, and I've drawn them. In total, there are 4 stereoisomers for that chiral molecule. Everything falls into place. Why? Because it passed the stereocenter check and it passed the no internal plane of symmetry check. Okay. How about this second case? First, we look for stereocenters. This is exactly one. I get a lot of students that tell me that these are meso compounds. But you know what? These are not meso compounds. You know why? The first thing you have to do is check for stereocenters. These do not have stereocenters. Take a look. Don't be fooled by wedges and hashes, okay? Sometimes we have to use wedges and hashes. These two molecules are in fact different from one another. They are different. One of them is cis with the bromine and the methyl both up. The other one is trans with the bromine and the methyl opposite to each other. They are not the same molecule. But they're not meso compounds either. Why? There is no stereocenter. It totally does not pass the stereocenter test. Yes, the hydrogen is priority 4. Yes, the bromine is priority 1. But just you try to break the tie as you go in either direction. There is no tie breaking for priority for the other carbons. Thus, if you can't break the tie, it must be the same group. So it doesn't distinctly have 4 different groups, and you can do the same on the other side. You end up going around trying to break the tie, carbon CH2 to the next carbon, layer after layer, you end up at another, you just keeps getting tied. So there's no way to break the tie. It does not have any stereocenters. Therefore, it is not chiral. Both of these are achiral molecules. Okay, this is an achiral molecule. Not because it's meso, because it doesn't have any stereocenters. There's a difference. When something is predicted to be achiral, it's either going to fail stereocenters or it's going to have stereocenters but show an internal plane of symmetry. So that's why I say you have to do these checks in the order given. First, check for stereocenters. If it doesn't have stereocenters, it cannot be chiral. It is an achiral molecule. If it does have stereocenters, but you find an internal plane of symmetry, then you can classify it as a meso compound, which is also achiral.